Welcome back, students. We were discussing comparison of lanthanides and actinides and similarities which were observed in actinides and lanthanides. They were discussed, and there were five in number. On the basis of these five similarities, they were placed in the same subgroup, or that is called F block elements. And there were many other properties on the basis of which we were able to place or to categorize these two series in broadly in one group or one series. Then now coming to all differences, there are so many differences between lanthanides and actinides because the lanthanide and actinides they have different behavior on the basis of certain characteristics, and on the basis of these different behaviors we are able to differentiate them from each other. Binding energy of 4f electron is high for lanthanides, while the same energy is low for actinides. Now, these 4f electrons and 5f electrons, for which the binding energy is different, they will greatly affect the chemical behavior of lanthanides and actinides. And on the basis of this energy, binding energy, we are able or we would be able to explain certain chemical characteristics of these species. For example, if lanthanide and actinides with the same rest of the properties, for example, electronic properties are given, then they will observe or they will suffer from they will give different chemical behavior under identical conditions. So next is a greater shielding effect for lanthanide was observed for incoming for F electrons, and this shielding was poor in case of actinides. And on the basis of this shielding and 4f electrons and binding energy of electrons, we were also able to explain certain properties which were different from each other. For example, lanthanide contraction was quite regular, while this type of contraction was not regular in case of actinide, and that was probably because of these properties that shielding was not perfect in case of F, while that perfectness was also least in lanthanides and more in the imperfectness was more in case of actinides. Maximum oxidation state for lanthanide was +4, although +3 was common oxidation state for both actinides and lanthanides. If you remember lanthanides, they reached up to +4 oxidation state, and beyond +4 there were no element to found in the earth crust or in nature or in any of their compounds. While in case of actinides, this +4 is the least one, or we can say the oxidation state was ranging from +2 to +7, and this +7 is quite a high oxidation state. So, oxidation state of actinides can be higher than oxidation state of lanthanides, where +4 and +7 is the two extreme of both for both the series on higher side. Lanthanides do not form oxycations, while for actinide this was quite normal to afford oxycations. And once again, the formation of oxycation was based on high chemical reactivity of actinides and least chemical reactivity of lanthanides is in comparison if we compare them with each other. So actinides are more reactive, they exist in higher oxidation state, and this higher oxidation state was uh, uh, this it made the element or the ion able to combine with oxygen in order to give oxycation, which is not normal for other metal in the periodic tables even. Now, non-radioactive are lanthanides. There were hardly one or some members which were not naturally radioactive, but they were artificially radioactive. The only the promethium was radioactive in lanthanide series on the basis of certain phenomena which is required for radioactivity. While if you look at actinides, So most of these members are radioactive, and most of them are naturally radioactive elements. So lanthanides do not make complexes easily on the basis of chemical reactions or chemical reactivities, because the binding energy of 4f electron, which is higher, and removal of electron is relatively difficult. Greater shielding effect, which also cause uh, the lanthanide contraction in a proper way, and also this greater shielding effect will affect the chemical properties of the series. So lanthanides are least reactive metals, while actinides are more reactive metals. And on the basis of reactivity, if we make the complexes of lanthanides and actinides with pi acceptor ligands, so with pi acceptor ligands, lanthanides are unable to afford complexes, while actinides are capable to make complexes with pi acceptor ligands. And hopefully pi acceptor ligands we will start in few days in next chapter, inshallah. The lanthanides, they are paramagnetic, and their magnetic properties can be explained easily. If you remember again, here we discussed, or we took on board two properties. One was the spin contribution, and the other one was magnetic contribution. So on the basis of spin and magnetic contribution, we were able to predict the uh, magnetic properties of lanthanides theoretically, while the same formula then failed to predict the magnetic properties of actinides. And it was because that orbital contribution of actinide was quenched, and because of that quenching, the theoretical paramagnetic properties are theoretical magnetic properties, and actual magnetic properties were widely different from each other, which was not normal phenomena for lanthanides. Thank you very much.